Okay, hello and welcome back everybody. Calling this section worked examples for sets, maps, and functions. And we're just going to go through a few of the examples, kind of making a little bit more concrete what we accomplished in the last video. So we'll start with some examples of sets. First example that I have to work through is use set builder notation. And if we recall, what that looks like is two curly brackets separated by a stroke. And in the left-hand side, we have a collection of objects. And on the right-hand side, we have properties that they satisfy. So we'll use that notation to construct the sets. So let's look at our first one. Our first set is 1, 3, 5, 7, 9, and so on. These are the odd numbers. Our second set is ... -4, -2, 0, 2, 4, ... These are the even integers. Our third set is 1, 2, 4, 8, 16, ... These are the powers of 2. Our next set is an interval. So this is an interval with an open side on the left and a closed side on the right between the numbers -4 and e, which happens to be 2.718 ... Euler's constant e. And our last example is 0 to 1 open and 1 to pi, where we close the side of pi. So let's use set builder notation on each of these, and that's kind of to make it more concrete what these ellipses mean. Every time we write these down, we have ellipses sitting around, and that can be a little bit confusing because we're not actually being rigorous about defining the entire set, right? If we can use set builder notation, perhaps we're relying on the integers or the natural numbers or something, then we can get smaller, more concrete and rigorous sets that describe these cases. So with that said, with the odd numbers, what do we want to think? These are definitely all elements of the natural numbers, right? Recall the natural numbers are just our whole positive whole numbers. And so since they're all elements of the natural numbers, using set builder notation, we'll just write an n, right? Or we can say n in the natural numbers. So that's a collection of objects. But now we need to say that they satisfy something. What is a property that odd numbers satisfy? So we need to come up with some sort of property which odd numbers satisfy, and that's what's going to give us the ability to write this in set builder notation. So I think about it a little bit, and it's not too hard with even numbers. Even numbers is quite easier. Even numbers are all multiples of 2. And odd numbers, if we want to be clever, odd numbers are all exactly 1 away from a multiple of 2. So that's what we'll write on the right-hand side. How can we construct, mathematically speaking, what it means to be 1 integer away from a multiple of 2? We can write something like 2k plus 1. This would be 1 away from a multiple of 2. Because 2k is a multiple of 2, and if I'm adding 1 to it, that means I'm 1 away from a multiple of 2. So 2k plus 1 is equal to n. That's a property that n needs to satisfy when k is in, we could say z, we could say n including 0, or whatever we want. We just need to specify that k in particular is going to be constructing the multiples of 2 with us. So this is pretty cool. We're saying we're sitting in the natural numbers, which all of those are. And more than that, every one of us that sits in the natural numbers is exactly 1 away from a multiple of 2. So this is kind of how we use set builder notation. We just have to get clever about the properties that our objects that we're concentrating on satisfy. Of course, that means the even integers get way easier, right? The even integers, knowing that we're able to construct 1 away from a multiple of 2 for the odd positive numbers, evens should be really, really easy. So we can just say these are the numbers in z which satisfy, they're not 1 away from a multiple of 2, they're actually a multiple of 2. So this just means 2k is equal to n when k is in z. So that's going to be the construction of the even integers. And you'll notice we're specifying that we're in the integers right away instead of natural numbers right away, depending on what sort of subset we start in. Powers of 2 maybe are a little bit tricky, but it shouldn't be too bad. We can say, notice that all of these are still elements of the natural numbers. So as elements of the natural numbers, we can just say hey, I'm n in the natural numbers. What property do I satisfy? I satisfy that I am a multiple of 2, or a power of 2, I should say. Satisfy a power of 2. That means n is equal to a power of 2, 2 to the k, when k is in. Now I could get away with z or n once again. You can even say k is in r, right? Because the fact that we're quantifying over our original set, the natural numbers, there's only specific cases when that's going to be true. So we'll just say k and z again there. And so there's 3 nice examples of set builder notation. These are kind of with our discrete sets where we're not working over the reals, but now we have 2 cases of the reals. And these basically are intervals, right? We've got kind of intervallic notation going on there, but we've drawn it out maybe figuratively rather than explicitly. So if we're going to do this interval, which is a subset of the real numbers, if we've got a subset of the real numbers there, how could we write that? Well, for a subset of the real numbers, I'll say we're x in r, because we're a subset of the real numbers, such that, what's the property that these x's satisfy? Well, they're definitely going to be greater than 4. X is greater than 4, and it's less than e, but because we're including the endpoint here on e, it's going to be less than or equal to e. So we can just use both of these, and we can combine them together if we want. We can say 0 or 4 is less than, negative 4 is less than x, which is less than or equal to e. And we can construct that as our set builder notation version of this interval. We can do the same thing below, right? So below we have over here x is less than 0, x is going to be, or greater than 0, x is going to be less than 1, x is going to be greater than 1, less than or equal to pi. So write that in set builder notation. Definitely working in subsets of the reals. I'm greater than 0, and I'm less than 1. Now I have to use this word or, right? So the word or is going to be special, and that's because I have a case of both gives the word or. I don't have to satisfy that I'm in both at the same time. I have to satisfy that I'm in one or the other. That's when we use the word or. And I'm going to be greater than 1 and less than or equal to pi. And so there's my set builder notation for that final collection of intervals. Okay, moving on, we can construct an example of functions. And let's use a function that we're all quite used to. So let's stick with f. And recall the way that I define functions. This is the way that most mathematicians do. So we're going to have a domain is going to be the first set that we write down, and then the codomain is the second set that we write down. Along with, so we say f is a function from r to r defined by, and then we construct its rule, right? And the rule is kind of this mapping where we include an argument, and then wherever the argument ends up. So we've got the function mapping the reals to the reals, and the rule is that when you place the argument x into f, you end up with cosine of x. So what are we going to do? We're going to identify, the example here is to identify the following objects, right? Identify the domain, the codomain, the range. We're going to ask, is it injective? Is it surjective? And let's go ahead and make my life a little bit more interesting and say, let's find the image of the set 0, pi, and 2 pi. So we can just construct that set of three elements, 0, pi, and 2 pi, and find their image. So to identify the domain, it's really not bad, because in all of these problems, really the domain should be given to you. And I know, like I said before, if you're in pre-calculus and calculus, that wasn't the way things behaved. But from now on, you should really expect to always be handed the domain. And all you're looking for is after the colon, which identifies the function, it's going to be the first entry is going to be his domain. So in this case, the domain will be R. To identify the codomain, we look at the second entry. That's really what the arrow R to R means, is we're going to look at the second entry there. We're going to say the codomain is also R. Now the range is the tricky one, right? Because the range, if you recall, is the collection of all outputs. And I'll put that in quotes for you here. So let's, to try to understand the range, let's graph. Let's graph this function. So on the xy plane, if there's x, there's y, which happens to be the image, f of x. Function cosine looks like the following. So if you don't remember, that's basically what cosine looks like. It continues up and down, oscillating between the values of 1 and -1. These are the y values, indefinitely. So it's going to oscillate between those two numbers indefinitely. So to find the range is the collection of all outputs. Where are the outputs here? The outputs are the y-axis. So what is the collection of points hit on the y-axis? Range equals collection or really set, right? This is why we're working with set of points hit on y-axis. So not intersecting the y-axis, what we're doing is we're thinking about projecting the entire image, right? When I write my plot here, I'm thinking about projecting everything onto the y-axis. And when I finish that projection, I'm asking what is the interval on the y-axis that's being hit by this function. So what we can write here is what is this interval that's being constructed along the y-axis. Note that because 1 and -1 are both being hit, we're going to have an inclusive interval, sorry, closed interval, and everything in between the two of those are being hit. So with all that said, the range here is the closed interval from -1 to 1, also known as the set closed -1, 1. You can use set builder notation if you want for that as well. But that's going to be the range here. Is it injective? Now let's remember what this word injective means. So let's see, what does the word injective mean? Injective means f of x equals f of y requires that x equals y. So what does that mean with regards to our function here? Let's say, suppose cosine of x equals cosine of y. Now let's be careful. I have a good habit of using y there and y there. Those are not the same thing. Okay, so the xy plane that gets constructed just means that we have two orthogonal axes. When I write this whole x equals y at the bottom here, that one, I'm not saying that I'm looking on the xy plane. What I'm saying is that I'm placing just two independent numbers into my function, and I'm asking whether or not the numbers that got placed into my function started out the same. Okay, so these do not, this y does not have to do with not xy plane. Okay, we mathematicians like to use the same letter for all sorts of things, and we expect the listener to know from context. And I realize it's not the easiest thing in the world to do, but you should get used to it the more and more you see this. So f of x and f of y, just two different inputs, two distinct inputs to my function. Suppose that they're equal, the outputs are equal. Do I require that the inputs were equal? So does that require that the inputs are equal? Do I require that x was equal to y? And it's pretty easy to check that no, I don't. One really easy example is that cosine of 0 happens to be equal to 1, but cosine of 2 pi also happens to be equal to 1. We jump over to our unit circle. You'll think about every time you travel around the unit circle, that's a traveling of 2 pi, and of course the x value, the cosine value, is equal to 1 there in both cases. And so I'm not requiring that that input and that input are the same for my output to be the same. The fact that 0 and 2 pi are not the same input, different inputs, but same output. So no requirement that x equals y. No requirement that the two inputs had to be the same if the output was the same. That means not injective. So we'll say no here. Next question is about surjectivity. So is my function surjective? Let's recall what surjective means. So surjective means that it's really actually easy if you've already identified your range. Range equals codomain. That's it. And so all we do is we look at our range, we look at our codomain. My range is right here, -1 to 1. My codomain is r. Is r and -1 to 1 the same? No, it is not. So because r and -1 to 1 are not the same, and of course I switched the order, but that's okay. Since r and -1 to 1 are not the same, then the range and the codomain are not the same. Not surjective. So I just say no here as well. And then finally, find the image of the set 0, pi, 2 pi. It's just asking me to go ahead and compute the output of the function. So just the image is just the set of outputs of a specific set. Okay. So I'm just looking at that specific set here. I'm going to compute the set of outputs. And that's not really the hardest thing to do. All I have to do for that, I'll go over here and I'll say f of, and I just place it like this. You'll see mathematicians use this notation. They'll place the entire set in there and say that this is cosine of the entire set as well. And the nice thing about these is that they are always able to pass through, so the cosine is always able to come onto the inside, 2 pi. And now I just compute those three numbers. Cosine of 0, go back to your unit circle, that's 1. cosine of pi, that's moving pi times around the unit circle, which is half of a unit circle. That's equal to the x value there, which is -1. And all the way back around to 2 pi gives me a value of 1. Now, the funny thing about sets is that this is a valid set. This is totally a viable answer if you want it to be. You can make your life easier if you want. Because we have 2 copies of 1, only 1 is necessary. 1 copy is necessary. So you don't need to include both copies of 1 in your image if you don't want to. You could just reduce this set down to 1 copy of the positive number 1. Either one's fine though. There's definitely no harm in adding extra terms, but I'll just write this as 1 comma -1. That is the image of the set that we have in mind. That's a nice example with a function. Let's move on to another example with a function. Suppose now we have a new function, f from n into r, defined by f of n equals m divided by n plus 1. We're going to identify, just as before, the domain, the codomain, the range. We're going to ask ourselves whether or not it's injective, whether or not it's surjective. And I'll skip questions about images here. Images aren't quite as important. So let's go ahead and identify the domain. Well, just like before, it's almost always given to you. It's just the first entry there. The codomain, similarly, is the second entry there. The range, we get to be a little bit clever. This will be a lot of fun. You could graph. Let's say I could, I'll put quotes in that. I could graph this, but the inputs are not continuous. Right, so it doesn't really make as much sense to plot this on a graph because you're only looking at the image of every natural number and not the image of every single x. I think it's actually to our advantage to calculate the image of the domain directly. So in some cases, it's really to our advantage to just calculate the image of the domain directly, which is always image, right? It's an image of a specific, so this is f of a set, and the domain is specifically the set n. Okay, so to do that correctly, the range is going to be f of the entire set n. For the entire set n, we can make our lives a little bit prettier and write it in set notation as 1, 2, 3, 4, ... And we can pass f through. This is f of 1, f of 2, f of 3, f of 4, ... So it's a set that contains all of those. And we can calculate all of that because we know what f looks like, right? We can calculate f of 1 because we know that's 1 divided by 1 plus 1. So let's go ahead and do that. So that's going to be 1 divided by 1 plus 1. This is going to be f of 2 is going to be 2 divided by 2 plus 1. F of 3 is 3 divided by 3 plus 1. 4 is 4 divided by 4 plus 1, ... And we simplify things a little bit. What does this look like? This is 1 half, 2 thirds, 3 fourths, 4 fifths, and so on. And so it's interesting to say that actually in some ways we could go ahead and run some set builder notation on this, but in some ways this is the range. So like we should really just write it out as the range is 1 half, 2 thirds, 3 quarters, 4 fifths, and so on. If you want to see me run a set builder notation here, it's really quite straightforward because we know what f looks like. We already have kind of written out f. The set builder notation just uses that. So we just say n divided by n plus 1 such that n is in the domain. So there's your set builder notation if you want to take it instead. But either version is good for the range. Now let's ask this maybe trickier question about injectivity. So as before, injective asks if f of, we're using n here as our input. So if f of n equals f of m, so I'm going to this is my new version of 2 inputs. I'll use the letters n and m, so 2 distinct inputs, requires that n equals m. So we're asking that question for injectivity. And the best way to do this is to write things out explicitly. So let's just go ahead and write it out explicitly. That's n divided by n plus 1. And then the equal sign comes down for free, and we have m divided by m plus 1. Does that identity require that n equals m? Let's see if we can make it happen. See if we can simplify. So let's see if we can simplify the expression into n equals m. if we can pull off a simplification of this expression into n equals m, then we find out that we are injective. So let's try. So we'll cross multiply. That's what happens when we've got fractions equal to each other. So now we have n, m plus 1 equals m, n plus 1. We can distribute everything. So we have n, m plus n equals m, n plus m. And what do you know? So that's the left-hand side is nm. The right-hand side is mn. What we can do is subtract both sides, mn, and things are going to cancel. What are we left with? N equals m. Voila. So what we found out is that actually if you start with the two things being equal to each other, you do actually require that m is equal to n. Really quite surprising that you can just simplify it to that case. But because we have this as a requirement, we have injectivity. If I can spell injective. So that's pretty cool. That's how you can show that some functions are injective now and then. So we'll say yes here. And then finally we have questions about surjectivity. Surjectivity. Let's see if we recall the definition of that. Definition of surjective is that the range, so surjective is, does the range equal the codomain? Well, we've identified the range, we've identified the codomain, we just have to check once again. So here's our codomain, here's our range. That's missing a lot of real numbers. I mean, for example, 0. 0 is a real number that's not in the range. And so if you can even identify a single real number that's, in the codomain that's not the range, just say note, 0 is in R, but not in range, hence not surjective. So all you have to do is identify one case where it's violated, and you're already good to go. You could have chosen pi, you could have chosen e, you could have chosen the square root of 2, you could have chosen negative 45. None of them are in the range, and as long as you violate that in one situation, you are not surjective. There's a second example of questions about functions. We're going to move on to one more, and then we'll finish up for today. So this last example, we're actually going to give ourselves two functions. So we'll say let g be a function from R into the set. And here I'm using interval notation, 1 to infinity. We always put an open bracket by infinity. We say it's basically because you can't reach infinity, so every number is strictly less than infinity. That's why we use the open bracket there. So we're going from R to, this is really kind of like a positive, every positive number greater than or equal to 1 as our codomain, be given by, and so g needs to be associated to its rule, and the rule for g will be x squared plus 1, and then we'll define another function f, so we'll say that f actually goes from the codomain of g back into R, be given by, let's make f of x's rule the square root of x minus 1. And now what I'm going to say is compute f compose g and g compose f. So this is us getting a little bit of an excuse to compute some compositions. And actually I'll say, how do they compare? This is going to be a nice little hint at where we can head eventually in this course. Let's go ahead and compute f composed with g. So let's recall the definition of f composed with g. Well, because it's a function, it needs two things. It needs its domain, and it needs its codomain. So let's identify those first. Well, if we think about it, what's the input going to be? I'm going to input something to g. So I'm looking at the inputs of g for my domain. Inputs of g. Well, the inputs of g are R. So that's coming down as our domain. And the codomain, let's see where I'm outputting. I'm outputting f. Okay, so my codomain is going to be the output of f. So then I can grab this R as my output of f. So there's my domain and my codomain. F composed with g goes from R to R. Now let's go ahead and compute its rule. The rule is f composed with g of an argument x. And we actually just compute it by saying this is actually f of g of x. So now when I think about it, this entire term, g of x, I'm going to place inside of, notice here I had whatever was inside of f goes into the square root minus 1. So square root, whatever was inside of f minus 1, that thing that was inside of f is now g of x. And if I want to compute g of x explicitly, I know that g of x is x squared minus 1. So this is the square root of x squared plus 1 minus 1, or the square root of x squared. And now let's keep in mind that a square root is by definition the positive square root. This is something that I actually struggled with a lot when I was in my early undergraduate career. The square root is defined as the positive square root. Now this is really annoying Why do we use the word square root if it's only defined as the positive square root? Just because if you wanted to find the negative one, just write plus or minus in front of it. So you have the ability to write plus or minus. The fact that we didn't write plus or minus, let's just assume it's a plus. That's all it is. If you want to consider both, start your problem with a plus minus. If you don't, just use the positive. So what we get out of here is if x were negative, then root of x squared, because it's the positive square root, is actually going to give me a negative x, because it's like 2 rounds of negative. Or in other words, if I don't want to write it as negative x, I could write it as absolute value x. And in fact, if x were positive, it would also give me an absolute value, because an absolute value doesn't do anything. So the square root of x squared is not x, it's always absolute value x. So that's going to be f composed with g. We can also construct g composed with f and ask how those compare. So let's look at g composed with f. It also needs a domain and a codomain. And just as before, I'm just asking myself the question, what was the input to f? The input to f was the interval. Let's recall it's the interval 1 to infinity. And in fact, the codomain of g, what was the output of g? The output of g was also the interval 1 out to infinity. And so if I look at the rule now, I can compute the rule of g composed with f by adding an argument to them. And it's computed as placing the function f into the function g. So the output function g here was that function x squared plus 1, except it's no longer an x on the inside. Right now I have an f of x on the inside. So I'm going to place the f of x on the inside here, and I'm going to get f of x squared plus 1. And I know what f of x looks like. F of x looks like the square root of x minus 1. So I'm going to square that square root and add 1 to it. And when you square a square root, you can get away with just canceling them because the square root was already positive. The square on top just keeps things positive. So since square root was defined positive, stays positive. So we don't have to play any games with the absolute values in the other direction. And I know that's really confusing, but it's life sometimes. Life can be confusing. We end up with x minus 1 plus 1, and then the 1's cancel, and I'm left with x. So how do they compare? That's one question I was asking. Well, in one case, we get the absolute value. And in fact, the domain and the codomain are quite different from the domain and the codomain in the other case. We don't have an absolute value in the other case. But let's think about why. So in some ways, these are inverses of one another. We're basically getting x out of this, which would be, the true inverse function. But they're not quite inverses, because when you extend the domain and codomain a little bit, you lose invertibility. But if you restrict the domain and codomain, then you recover invertibility. So that's really what I mean by how they compare. So I'll just answer this here. G of f is an inverse. Well, it's an identity. That's what I should say. It's an identity equal to x, right? F of g is almost an identity. Because the absolute value, the absolute value function really is the identity on positive numbers. It's just not the identity on negative numbers. But anyway, this is giving you a pretty good idea of kind of the way we like to manipulate functions in mathematics. These ideas are going to play a role the rest of the semester, just notions of trying to consider domains, codomains, and sets over and over again. So it'll be good to get this down before we get into more complicated stuff. Anyway, I'll see you in the next class. We're talking about complex numbers then. Bye.